I was on vacation last week and I needed to build the following circuit. As you can see, the circuit below has a NOT gate, also known as an inverter, has a couple of AND gates, and it has an OR gate. So I needed to build this circuit, but the only type of gate that I had with me were NAND gates. The good news is it can be done. Any circuit can be built using only NAND gates. So let's take a look. And just to refresh your memory, a NAND gate is the exact opposite of an AND gate. So of course, an AND gate, if I had an AND gate here, I would get all zeros. That's supposed to be an AND. I'd get all zeros, except the last case would give me a 1. A NAND gate, and this is the truth table for a NAND gate, is the opposite of an AND gate. So I get a 1 for every case, right? I'm just inverting this, except the last case is a 0. So this is my NAND output. This is an important slide, actually, so you might want to pause the video and copy this down. So on this slide, I'm going to show you how you can use a single NAND gate to build a NOT gate, how you can use 2 NAND gates to build an AND gate, and 3 NAND gates to build an OR gate. So let's look at them one case at a time. In this first case, I'm using 1 NAND gate, and let's say the input is X. The output of this, of course, would be X with a bar over it. That's what a NAND does. It ANDs it, and then it NOTs it. So let's see, if I split this up using De Morgan's law, which you know and love, of course, that gives me X or X, which is the same thing as X with a bar over it, right? Not X or not X is the same thing as not X. So here I've used a NAND gate to build myself a NOT gate. Let's look at the second case, and again, let's call the input X and Y. So coming out of here, I would have, of course, X, Y with a bar over it. That's what a NAND does. Now this second NAND gate is really acting like a NOT, so that gives me an X, Y with a bar over it, and another bar, I'm knotting it, right? So I took a single bar, I'm knotting it. Now, of course, I can cross these out, and that just gives me X and Y. So here I have made an AND gate out of 2 NAND gates, right? I'm just ANDing. At the bottom, I'm using 3 NAND gates to build myself an OR gate. And let's just quickly see how that works. So of course, coming out of here, I have not X. Coming out of here, I have not Y. Then I'm NANDing them one more time. So that gives me not X, not Y, ANDed together with a bar over it, which I can split up using De Morgan's. So that gives me not X or not Y, which of course is the same thing as just X or Y. So here I have built myself an OR gate out of 3 NAND gates. Again, you might want to pause this video and copy it down if you have not already. This is an important one. Now we are finally ready to build the circuit which I wanted to build, right? Remember this original circuit here, this guy up here, this is the guy that I wanted to build, but I was on vacation, so all I had with me was NAND gates. So here all I've done is I've replaced the NOT gate with a single NAND gate, and you remember how that works from the previous slide. Then I've replaced my AND gates, these are 2 AND gates, I've replaced them with 2 NAND gates each. And you remember how that works from the previous slide again? Hopefully you copied that down. And then finally, I've replaced the OR gate. Instead of using an OR gate, because I'm on vacation, all I have is NAND gates, remember that part? I'm replacing that OR gate with 3 NAND gates. So there I have done it. I have built my AND OR inverter circuit using only NAND gates. But I'm going to even do one better than that. So stay tuned for the next slide. So this top circuit, of course, is the circuit I had on the previous page. And I noticed that really this is a NOT gate followed by another NOT gate. So this is really just like saying I have not X knotted, right? 2 NOT gates in a row are the same thing as just X, right? I can cross these dots out. So if you see that you have a circuit with 2 NOT gates in a row, you can cross them both out. You can only cross them out in pairs, of course. Like here's a NOT gate, but I'm not allowed to cross that out because it's not followed by another NOT gate. just to be clear again, a NOT gate built out of NAND gates looks like this. It's a single input splitting into two NANDed. That's it. So if you have two NOT gates in a row, you can cross them out. And here again, underneath, I have a NOT gate followed by another NOT gate, so I can cross those out as well. So really, I could just connect this to the last gate and connect this to the last gate as well. And finally, underneath, I have redrawn it simplified, and you can see that I have done this entire circuit with just 4 logic gates. Finally, on this last slide, I'm showing the original circuit. Now, of course, the original circuit is made with a NOT gate, 2 AND gates, and an OR gate. Now, this would require 3 chips, right? Because one chip contains only one type of gate. So I would need 1 logic chip for this, right? An inverter chip. I'd need 1 logic chip for my AND gates, and I'd need 1 logic chip for my OR gate. Well, that's a lot. 3 chips to build this thing? Underneath, you know that I have 4 NAND gates on a single chip. So I could build this entire circuit right here using only 1 chip with just NAND gates, 1 chip. So not only am I having a good time on vacation, but I managed to rebuild my 3-chip circuit using just 1. I don't know why I wrote 1 chips. I think I can write 1 chip. So sometimes, this is not always going to be the case, but sometimes implementing a circuit with only NAND gates actually ends up saving you chips. This would actually save me money. If I were building 1 million of these circuits, I could actually do it with a whole lot less chips. And there you go.